Hey, BC Calc, we are up to day 80 here. Day 80 is some more exponential modeling. And I think you'll find it's very similar to the other exponential models that we've looked at so far. Maybe just a few additional constants thrown in there. So we're going to talk about something today for the first time called Newton's law of cooling. Maybe you've seen that in other applications, including physics. But to get started, there are 4 derivatives at the top and actually 1 integral thrown in there, number 4. Go ahead and try those for me. Those should go pretty quickly if you're pretty up on your exponential derivatives and log derivatives at this point. So we'll go over those next time we're in class. If we jump to the bottom, as a quick recall, it says the growth or decay rate is proportional to the existing amount present. So when that's true, we know that the rate, we'll call it dy dt, is equal to some constant of proportionality k times the amount present, which we typically denote as y. And what we saw a few days back is that if we are able to separate this and then create a separable differential that we then integrate both sides on, we get down to that very familiar form of an exponential model that we've used in prior years of math. So I'm going to separate this and put the dy over y and bring the dt to this side. So that this way, when I integrate both sides, we know the integral dy over y is the ln, absolute value of y. On this side, you would get, since k is a constant, kt plus c. And again, remember that technically, I guess when you find the indefinite integrals, it'd be plus c on both sides. But we can kind of swing all the constant and just leave it on one side there. And then after that, we're going to go ahead and convert this to exponential form. So we would have y equals e to this power, kt plus c. Remember that the reason why we're okay kind of to drop absolute value in this next step is that the initial amount or the existing amount present is going to be a positive amount. So we don't need the absolute value there necessarily. Remember that e to the kt plus c can be expressed as, using rules with exponents, e to the kt times e to the c. All right, because if you multiply 2 things to the same base, you would add those exponents. And the reason why we want to make that separation is that e to the c, therefore, is just a constant. So if we have all that information, we get the equation y equals. I'm going to bring that constant to the front, and we usually denote that with y sub 0 using some initial conditions, which represents the initial amount. Okay, so this is kind of just building that general model just one more time, because we're going to use this exact model in some of the following examples. So if you turn to the next page, based on what we've done with exponential models so far, I'm fairly confident you can do example 1 and example 2 on your own. So if you're feeling confident, go ahead and hit pause and try those and check back in with me in a moment. But let's take a look at the setup for each of these. So initially there are 10,000 bacteria and the population doubles every 3 hours. Find the growth constant k. So whether you want to use y equals y sub 0, or I feel like for a lot of these, I use n equals n sub 0 for the number initially and the number that's left after a certain amount of time, that's kind of up to you. But as long as you know where to sub in, if initially there are 10,000 bacteria, that's going to be n sub 0. We're trying to find k. That's going to be the growth constant, and it doubles every 3 hours. So when time is 3, we know that the end amount on this side is the doubled amount of 20,000. And as soon as I sub all that in, this is a really quick algebraic process to get k alone. Divide both sides by 10,000. And of course, because we're doubling, we're going to get a 2 there. So if 2 equals e to the k times 3, or e to the 3k, take the natural log of both sides. ln of 2 would equal 3k. And therefore, the growth constant is the ln of 2 over 3. So we can figure out what that rate is as a decimal approximation if we wanted to. But in the next example, part B says determine the exponential model for the situation. So in general, if I come back to this model here and I plug in now my new value of k, we know that the model would be n equals the initial 10,000, e to the k, which is ln of 2 over 3, times t. So now we can model that after any given amount of time has gone on, what amounts of bacteria we should expect. Now, you can kind of clean this up a little bit because we know that e to the ln, that those are inverses, but kind of we've got that 3 in the way right now. So just to kind of see an alternate form of this same equation, if you rearrange that exponent up there to be the following, if you make it e to the ln 2, and then raise that to the t over 3, right? Kind of take the 3, slide it over underneath the t here, and of course a power to another power, we would multiply those. So we would get the same exact expression that we have here. This is just kind of a rewriting of this. We know that e to the ln of 2 is just 2. So it will make sense that when I rewrite this, if we're doubling, that the base of the exponential function here is a base of 2. So 10,002 to the t over 3 power is another way to model the situation. But if we wanted to know the growth constant, we do have to go through this process of using our initial model that we've determined from having the rates, which is proportional to the existing amount present. Okay, here's another example. And again, even though maybe we haven't done one quite exactly like this yet together, half-life is something that I think you're pretty familiar with from chemistry. And certainly you talk about half-life in other math courses as well. So the half-life of a certain radioactive isotope is 5 years. How long will it take until only 1% of the original is left? So in order to figure this out, we have to figure out that value of K. What's the decay constant to get started? And you're not given an initial amount. But it turns out it doesn't matter. So whatever the initial amount is here, when I plug in 5 years for the time, I know that on the other side where the end amount is, 5 years later, we have to have half of the initial. So no matter what you pick here for n sub 0, the other side is definitely half of that, n sub 0, which means that when we do that initial step of dividing both sides by n sub 0, you're always going to get a 1/2 on this side. So if 1/2 equals e to the 5k, we get a really quick ln and ln on both sides. So ln of a half equals 5k. And then k equals ln of a half divided by 5. And I know you might be used to other ways, and again, especially from chemistry, I know you deal with half-life, so there are other algebraic ways of solving this, but this is definitely the approach I'd like you to take based on what we've talked about in this unit. So from there, how do I determine how long it will take until only 1% of the original is left? So I want to figure out the time that it takes for the end amount to be 1%, 0.01 of the original here. So on this side, we would have, again, it doesn't even matter what the initial is. This side's going to be 1% of the initial. E to the k ln 1/2 over 5. And then we're solving for time here. It looks like we have too many variables, but again, we're just going to divide the n sub 0 out. Okay, so when I divide both sides by n sub 0, we get 0.01 equals e to the ln of 1/2 over 5t. Probably a few different ways to go about this. I kind of like taking the ln of both sides at this point, because I know ln of this side is just going to leave me with the exponent, ln of 1/2 over 5 times t. And then to get t alone, I'm going to multiply both sides by the reciprocal real quick. So that's going to be ln of 0.01 times 5 divided by the ln of a half. So let's see how much time it takes until we only have 1% of the original substance left. So we've got ln 0.01 times 5 divided by the ln of 1/2, or just 0.5 there. And it takes approximately 33.219 years to 3 decimals. And there you have it. Okay. All right, so that was just a little bit of practice using some of the exponential modeling equations that we've seen over the past few lessons here. The last part of today is going to be a new model, and the new model is for Newton's law of cooling. So for Newton's law of cooling, it's defined as the rate at which an object's temperature is changing is proportional to the difference between the object's temperature and the temperature of the surrounding medium. So we have a rate proportional to a difference in two temperatures. So that's going to wind up being an exponential model that we can derive by doing the following. Well, first of all, I've defined that capital T is going to be the object's temperature at time t, and then T sub s is going to be the surrounding medium's temperature. So according to Newton's law of cooling, the rate at which the object's temperature is changing. So the object's temperature is capital T. Now, if you love the variable t, get ready for it because there's going to be a lot of t's in this one. But d capital T dt would equal, it's proportional to some constant k to the difference between the object's temperature and the temperature of the surrounding medium. So it's proportional to that difference. And then once we have this set up, T minus T sub s would really just be a constant, right? So if we wanted to derive what's going to be Newton's law of cooling, we could actually use a quick dummy variable. Let's let y equal the difference T minus T sub s. And then we get that dt would equal k times y. And actually, if we go ahead and think about what this relationship implies, when the rate is proportional to an amount present, we know that this eventually turns into y equals y sub 0 e to the kt. Okay, we proved that at the start of the lesson today, so I don't think we have to go back to do that. But if we know that this is the model that it's going to turn into, where y is the difference between T minus T sub s on this side, we can replace that T minus the temperature of the surrounding medium. And then over here, when we have y sub 0, I'm just going to introduce T sub 0, which would be the temperature initially minus the temperature of the surrounding medium times e to the kt. So just where T sub 0 is equal to T of 0. It's the initial temperature of the object. Okay. So this formula might look familiar to you. Again, I can think of other times in, pre-calc and maybe algebra 2 as well, where we use this exact formula to describe Newton's law of cooling. But where does it come from? Well, it's really just a derivation of that same old rate proportional to an existing amount present. And we very quickly get to Newton's law of cooling here. So as an example, a hard-boiled egg at 98 degrees Celsius is put into a sink of 18 degrees Celsius water to cool. So what we know, if it's originally at 98 degrees Celsius, that's going to be our T sub 0. And it's put into a sink of 18 degrees Celsius. So that's the temperature of the surrounding medium, T sub s. Okay, so let's define all our T's here. And then after 5 minutes, the egg's temperature is found to be 38 degrees Celsius. So when T equals 5, we know that the temperature, which is just good old normal capital T, is 38 degrees. Assuming the water has not warmed appreciably, how much longer will it take the egg to reach 20 degrees Celsius? Okay. So we're going to take the information we're presented with at first and find that value of k. And that's what all these problems are really about. I mean, if you look at the last two, finding the growth constant or the decay constant, and then once I find that information, we can use that to do the follow-up of figuring out how much longer, and that's actually something we'll have to pay attention to, will take the egg to reach 20 degrees Celsius. So I want to figure out what time does it take to get to that new capital T of 20. Before we can get there, let's find the value of k, and then we'll go ahead and use that value of k to answer the follow-up. So if I plug in everything that I know into Newton's law of cooling right here, capital T to start is 38 minus T sub s, which is 18. That equals the difference. T sub 0 is 98 minus the surrounding temperature of 18. E to the k times, we know this happens when k is 5. We've picked some nice numbers here, right? This difference over here is 20. The difference on this side is 80. E to the 5k. So if I divide the 80 out, we get 1/4 equals e to the 5k. And then take the natural log of both sides, just like we've done in all the others. So therefore, k winds up being the ln of 1/4 over 5. Okay. Now that I know this value, this constant for the rate, we're going to apply that over here where we're looking for what's happening when capital T is 20. So since we know the value of k, what's little t when capital T is 20? So when I plug in 20 for t, we're going to get 20 minus 18 on this side. And again, the initial is still the 98 minus 18 over here. E to the k up ln of a quarter. I squeeze this in here over 5. And we're solving for how much time does that take. Okay. So from here, we're going to get 20 minus 18 is 2 equals the 80 e to the ln of a quarter over 5t. Divide the 80 over, so that's 1/40th. E to the ln of a quarter over 5t. Like I did in the last example, we're going to go ahead and take the ln of both sides because I know that that's going to drop down this exponent here. So the ln of 1/40th equals the ln of a quarter over 5t. And therefore t equals, and multiplied by the reciprocal, 5 times ln of 1/40th divided by the ln of a quarter. Let's see what this comes out to be. So the time it takes to cool to 20 degrees would be 5 ln of 1/40th divided by ln of a quarter. And that winds up being 13.305 minutes. Okay. So that's the amount of time that it takes to cool from the initial temperature of 98 degrees. Okay. But remember, the question says, how much longer will it take to get to 20 degrees? Because we know in the first 5 minutes, that's how long it took to get to 38 degrees. So how much time has elapsed in between when it cooled to 38 to 20? Just subtract out the 5 minutes that it took to get to 38 degrees. And we have that it took 8.035 minutes longer to cool to that amount. So not that it's a tough calculation in the last step. It's just important to remember to go back and answer the question correctly. Not just how much time does it take, how much longer did it take? And in this case, it takes about 8-ish minutes longer. So you'll notice that on the last page of your packet here, we have some day 80 homework, and these will be questions very similar to some of the exponential growth and decay models that we've seen. So go ahead and practice with those. We'll get some answers eventually, and we'll be preparing to take a quiz very soon on all of this information. If you have any questions about exponential models, specifically even Newton's law of cooling here, let me know next time I see you. Have a great day.